In one case, the ligand is participating, but not in a reversible way. In the other case, the ligand is participating reversibly. It's formed back and gets active again. And in the third one, the ligand doesn't participate at all. We have the classic olefin dihydrogen activation. There's different classes of complexes that are classics for this. I don't dwell too much on this. Perhaps just emphasizing a bit the difference. So the one class complex is Wilkinson's catalyst, which is undergoing the classic dihydrogen activation by an oxidative addition. I'd like to point, and this has been one of the most studied, best studied catalytic systems, so we know quite a bit about the mechanism as well. And this is a simplified presentation. There's many equilibria that play a role, and actually you can have oxidative addition already here, and then you enter to this species via a slightly different mechanism. The important parts, I'd say, is that typically you need here, there's the classic activation, a phosphine that has to depart. Those of you that remember trans effects and trans influences, they are agreeing that this is the wrong phosphine that departs. So this is not electronically driven, but sterically. The three phosphines are really building up steric pressure, and so it's the middle one that is the easiest to be released. And then this can be replaced by dihydrogen. So we get the dihydrogen on the XY plane and not on the Z axis. So it's not the hydrogen that absorbs here, because this is rhodium 1D8. So the Z square cannot bind dihydrogen. So what is important? We first have oxidative addition of dihydrogen. We form an octahedral complex. This is a bit sterically crowded, but now here the solvent can be replaced by an olefin, and then we get in a rate-limiting step, we get migratory insertion, so the olefin inserts into one of the rhodium-hydrogen bonds. From here it all goes fast, the alkyl complex is not stable. Either it goes back to the dihydride, or more productively it forms the reductive elimination process and regenerates the solvento complex here, which can then, and that's the big advantage of phosphines, they're very stable. So the catalyst goes back to this system here. The resting state of the complex is as well, of the catalyst is as well the starting point of the reaction. I'd like to point out again the sequence of events. First oxidative addition, then olefin coordination, then the rate limiting step. Well, here's some of the complexity. I don't dwell too much on it. The nice thing about about Wilkinson's catalyst is then that you can play easily games of tunability. You can look at activity depending on the phosphines, and you'd see that principally the stronger donating the phosphine is, the higher the activity it is. The more sterically crowded the phosphine is, the lower the activity is. And we should be able to rationalize both effects. Stronger donation of the phosphine means that oxidative addition is easy. Steric crowding means the rate determining step is hindered. The more steric crowding we have here, the less migratory insertion needs space. So that's prohibited. Then the second important hydrogenation catalyst that I like to quickly talk through is Crabtree's catalyst, which is based on iridium, a cationic iridium species, again iridium D8 complex, which is very close to the active species already, because you can consider this cyclooctadiene complex as a system that has the substrate already bound. So it's almost like a system on the catalytic cycle that can activate, they can bind dihydrogen, get reduced, maybe not as cyclooctadiene, but actually as cyclooctane. So you get this square planar complex. And now the events, the sequence of events is inverted. So you first have olefin coordination. Here I've drawn you a chelating olefin. Chelation, that's maybe chelate stabilized. And only when the olefin is bound, we get oxidative addition. This has significant consequences, because if you look at the scope of the catalyst, you'd see that Wilkinson's catalyst is not coping with sterically hindered olefins. Trans olefins are not that great. Tri and tetra substituted olefins are essentially not converted. In contrast, Crabtree's catalyst is way more tolerant and way more active towards a number of olefins, including sterically very hindered olefins. So that provides some, if you like, with Wilkinson's catalyst, some selectivity, with Crabtree's catalyst, some scope of hydrogenating as well, very hindered olefins like in steroids and the likes. Very interesting for pharmaceutical applications. I've shown you here the turnover frequencies, and you'd see there's a dramatic difference. And even so, the catalyst, Crabtree's catalyst works at lower temperature, there's this tenfold increase. So why the heck are we using Wilkinson's catalyst still, if Crabtree does it all but faster? What's Crabtree's catalyst? Why do... Some of you have... Who has used Wilkinson's catalyst recently? You. You did this dihydrogen capturing. G10 told me over lunch. So what is, why would one still use Wilkinson's catalyst rather than Crabtree's? So I showed you the selectivity, I showed you the turnover frequency. You remember the three aspects that characterize a good catalyst?
If you want to get a double bond alkene from a triple bond, that is a very difficult case, right?
Don't know about triple bonds.
No. If you have an alkyne, if you want to stop the reaction at alkene, then...
No, they're both not selective. I think they don't work with alkynes. Now, the semi-hydrogenation of alkynes would be a different topic, but yes, an interesting one. But so you recall what we talked, what makes a good catalyst? Turnover frequency, we look here. Selectivity, we look here. So what's the third parameter that is important? Rate is frequency. Robustness means turnover number. Exactly. So turnover number is I have to make sure that my third finger is the right one and not the wrong one. So turnover numbers is the third important characteristic. And that's exactly where Crabtree's catalyst lacks. It undergoes a relatively fast deactivation because the hydrides aggregate to form a trimeric species that is just a thing, can't get activated anymore, won't bind an olefin, that's it, done. Say?
That catalyst will be difficult to make because there is a possible ligand that will be gas sensitive, so difficult to handle.
Yes. So sensitivity is a thing, but that's a thing for both, really. You know. But the problem with the catalyst here is that in the presence of hydrogen, it slowly but steadily trimerizes to give a very stable, inactive species that reduces its longevity. While with Crabtree's catalyst, with Wilkinson's catalyst, we've seen that the resting state is actually the complex, because the phosphine is there, can coordinate and decoordinate. Here you see, once you hydrogenate off the cyclooctadiene, you have no stabilizer but the substrate. So once that substrate gets in low quantity, the iridium starts to do other things. So it starts to oxidatively add dihydrogen before the substrate is there. You have the iridium dihydride, which forms trimeric systems. Done, gone. So the problem with the iridium with Crabtree's catalyst is that you need relatively high catalyst loadings, and you cannot run the reaction more than, say, an hour or two. Maybe more like half an hour. And then the whole thing is done. So if you haven't finished the reaction by then, you better add a new catalyst. So there's the trade-off. And with many reactions we have these trade-offs, and it depends what you want to do, what you need to do. But if you want to have a robust system, Wilkinson still outperforms Crabtree's. But then in terms of selectivity, Crabtree offers more flexibility because you have that empty, that almost, this super underligated iridium system. that likes to coordinate whatever. So even a hindered double bond goes there. And then the third class of hydrogenation catalysts are the Noyori systems. I've shown you the one, the amine-amide system in the heterolytic activation of dihydrogen. The other one that he propelled are these binap type or diphos systems, where he showed that this works as well in a very asymmetric version. And this works with so ruthenium has the advantage that typically it's super functional group tolerant. Ruthenium is not that reactive, and that's a huge benefit, and we know this from olefin metathesis as well. So that's one of the big advantages compared to Schrock's metathesis catalyst, that the ruthenium has a very low affinity for oxygen, for amine amides, so it goes straight to the functional group that we want to target. So different chiral phosphines have been used. Have you talked about asymmetric hydrogenations? So there's a nice thing about asymmetric hydrogenation with these ruthenium diphos systems is that we get a very nice example of how the thing that we see is actually irrelevant for the catalytic reaction. So that's what Curtin-Hammett principles have postulated. So if we take these phosphine systems, if there's an ethyl bridge in the back between the two phosphines, the ethyl bridge can be either in such a zigzag or in such a zigzag. And you see that the structure of this, or the configuration of this ethyl backbone, directs the position of the phenyl groups on the phosphine. And it's these phenyl groups that provide the chiral pocket. So with these phenyl groups, we form what people often describe as quadrants. So if we look at the ruthenium in the middle, let's take that complex here. If we look at the ruthenium as in the middle, the phosphines in the back, but the phenyl groups point forwards out of the table. And here, the bulky phenyl groups are between 9 and 12 o'clock, and here between 3 and 6 o'clock. So here's the bulk. While this one here is empty, these two quarters are relatively empty. So up here is empty, and down here is empty. Here it's just the other way around, so there's no selectivity. But as soon as we put a methyl group on top of these ethylene groups, like here, we have either a diaxial configuration or diaequatorial. And we know from carbohydrate chemistry and other systems, the diaequatorial system is not stable, and this one here is way more stable. So now we impose chirality. Because now we have a C2 symmetric system. Now this lower part is stable and this upper right part is bulky. So now imagine an olefin or a ketone coordinating to that ruthenium center. It can only coordinate one way. Not sure I can do this. So if I coordinate the metal this way, the olefin, so that's my olefin with a bulky and a less bulky. Can you see it, or am I sitting in front of you? So if I take that olefin, if I coordinate it this way, it's nice because the bulky part is in the upper left part, which is empty, and the small part is in the upper right part, which is sterically occupied. If I flip this the other way around, now, so that's the other face, you'd see that if I coordinate it this way, I get the bulk onto the bulk of the phosphine. So clearly there's a preferred way of coordinating the olefin, yeah? And that's what you see. And this is, now here I made the phosphines, I abbreviated this, these are spols. So if you coordinate the phosphine, this one here, where the large substituent is in the empty square. That's what you see when you just add the substrate to your complex, to your catalyst. While this one here is disfavored because here the bulky phenyl group is interfering with the phosphine. So here is your catalytic intermediate. This one, you clearly see it, and we know then oxidative addition of hydrogen will be rate limiting, so of course this will be slow, so it makes sense that we accumulate. This one is the stable system, this is unstable, so this is the active species. Now what happens if you add dihydrogen now? If you add dihydrogen, this mutual trans configuration, or cis, is distorted because when you add hydrogen, dihydrogen has to add in a very specific way. Dihydrogen on a metal complex can only add in cis configuration because of whatever I've shown you. With the pi back bonding, we need that pi back bonding to be cis. We cannot have a trans configuration. So the diphosphine has to be cis. This chelating olefin has to be cis, the dihydrogen has to be cis. So what happens is that the olefin, this olefin here, has to rotate out. Because now they cannot be both in the xy plane, but one has to go in the z plane. And if you rotate this out, you'd see that here, where the thing was empty, it rotates out into the bulky phase. So this is not stable, this is hindered. While here, the steric pain or the steric penalty is relieved upon rotation. And the olefin actually moves into a easy configuration. And then we know Wilkinson's catalyst, rate limiting step is the migratory insertion. So it's only after here where we have the rate limiting step. But this is very fast because it releases strain and it forms. This one here is way more stable than this one here, and off it goes. So basically this one we don't see because this equilibrium here between the substrate-free and the substrate-coordinated species, the equilibrium is largely here. But then the next reaction is huge, has a huge energy barrier. So this is a classic WYSIWYG. What you see is what you get. No. You get this one here by spectroscopy, but then rapidly the thing goes this way, fast oxidative addition, reductive migratory insertion, reductive elimination. So you see one intermediate and you get the opposite product. That's been 30 years old, but still we get trapped by this. So, but that's just one example to make a point about the cycle I showed you and how difficult it is if you see something spectroscopically. This is a classic thing that is off cycle. It's not part of the cycle, but it can go back onto the cycle. So it's reversibly formed, but what you see is not related to the catalytic active species. So there have been many applications for direct hydrogenations, and you see some of the activities are really stellar. So it may be worth to calculate this out. You know, you can work with hundreds of kilograms here and tiny bits of iridium. And the interesting part here is that you're getting into activities that you don't have to worry now about catalyst recovery. Now this is an agricultural metachlor, is a herbicide, so the legal requirements are a bit lower than for pharmaceuticals, but fact is that you're sort of in the parts per million, parts per billion metal waste can be in the product. Now with these type of turnover numbers, you realize that you need 1 iridium for 1 million substrates, so you're already in the part per million or in the sub-part per million impurity. The same you probably know from olefin polymerization with Siegel and Atlas systems. They're so active that nobody worries about recovering the titanium. It's so low quantities, you just leave it in the plastic. It's a trace then, and unimportant trace. So that would be the other thing. If we can't separate the system, then make it so active that you don't have to separate it. But it has to be very low because you don't want to have with every aspirin or ibuprofen you're eating, you're accumulating a bit of iridium because that's bad for your diet, and then the next time you stand on a scale, you find yourself getting heavier and heavier because you have your iridium somewhere. Kind of like not good. Anyway, so asymmetric hydrogenation there have been different concepts. The diphos and chirophos and the likes are one concept. Another one has been the chiral poisoning of systems, where you use a substrate-like poison that has a certain chirality. So it preferably binds to one enantiomer but not to the other one. So you basically, even if you start with a almost racemic mixture of catalysts, you poison one enantiomer so the other one goes fast. So you still get very high induction. And then the second one is the non-chiral amplification, which is a concept that is very interesting but more random than designed. When you happen to see it, it's nice, but often the non-linear chiral amplification can go both ways, so that your catalyst has low EE and you get much higher product EE, but it can as well go the other way around, because it could be that your chiral pure system gets deactivated by dimer formation, and then you basically have the racemate in solution. What are challenges if you need to write a research proposal? Here are some hints, not that I know how to tackle them, but these are challenges certainly to look at. One is to use asymmetric hydrogenation in the absence of functional groups. Here you see some functional groups, but the lower the coordination ability of the system is, the more difficult it is to discriminate the Re and the C phase of the double bond. So that's still a challenge. Some systems are very good, some are not so active. Another challenge certainly is the activation, the hydrogenation of benzene or aromatic systems. Typically, I'm dismantling everything. Typically, if you see hydrogenation of benzene, typically this is like an indicator for heterogeneous catalysis. So most of the time, if benzene is a substrate, this is a classic reaction feature of heterogeneous systems. If you have a homogeneous system, you'll be a hero. That goes for sure to JAGs. So that would be nice. Now, to show that you have a heterogeneous system, the best way to go is to use deuterium rather than hydrogen. If it is homogeneous, your deuterium is constantly being attacking from the same side. So the benzene is either eta 2, eta 4, or eta 6 bound, and then the hydrogen is constantly drifting from the metal center to the benzene, but so this is like a plate that gets attacked always from the same bottom side. So your product, if it's homogeneous and it's all staying at the same metal center, your product should have all thin isotope ladles, because everything comes from the same side. If it's heterogeneous, that means you get cyclohexadiene that releases from the surface, it binds, rebinds, you get cyclohexene, releases, rebinds, you get cyclohexane. But then always two hydrogens are on the same side, but the others are then random. So you should have two syn, two anti, and then you may have isomerization that the 1,3-cyclohexadiene becomes 1,4-cyclohexadiene, and so you get all types of scrambles. So benzene hydrogenation, or indeed any aromatic system hydrogenation on a homogeneous level, is still a challenge. That's an easy challenge, I hope. So having thought through all this, we can have different precursors to this steroid. This steroid can then be transformed to the fully saturated product. I would assume you'd easily spot what catalyst you could use for which of the transformations. First would be spot the difference. So we have like 4 almost equal systems. I'll help you with this one because that should be the challenge. The challenge should be which catalyst. So here we have this double bond here that gets here hydrogenated. Here we have this ketone that gets hydrogenated. here we have this allylic double bond that gets hydrogenated. And then here we have this double bond here that gets finally reduced. So what's the suggestion for which catalyst would you use for what type of transformation? Do you remember the catalyst? It's a bit hard without the notes, but then I hope some of the catalysts were not too unfamiliar to you. Any suggestions? Let me know. I take anything. There's no wrong answer. We will vote on each answer, so there's always a majority. But then that doesn't mean that that's then the non-Swiss part. In Switzerland, typically the majority wins. Here, this is more about science, so it may not be that the majority wins. Okay. Imagine I'm a rich pharmaceutical company. I ask you to consult me. I have these problems. You get paid when it works. You may get paid very well. So you don't want to miss that chance. Taking suggestions. Are you happy with your colleague's suggestion? Or your colleague agrees with your suggestion? Or not really? Who has consensus with the nearest neighbors? What is the consensus? You know, the good thing is you can be the spokesman of your cluster. So that doesn't mean it's your opinion. It's just, you could have opposite opinion, but because you're the spokesman, you have to. So you won't get rated, you won't get disqualified or qualified. There's no postdoc position associated with an answer, and there's no poor exam associated with an answer, so really you have nothing to lose.
I would use a bifunctional catalyst catalyst for B.
B?
For B.
Noyori,
Yeah.
you say.
Selectively the carbonyl bond will be hydrogenated.
For this one.
Yeah.
Okay? Okay. Which Noyori? Binap.
No, not the binder.
I mean diamide. So what's it? This one. Okay. Say? Binap for A. Okay. Other suggestions? Alternative suggestions? C? C, Crabtree. Is this spokesmanship or? See? just writing down. I'm not commenting. I'm not approving or misjudging. For D. Palladium and carbon. Other suggestions, as long as I can hear them still, or comments, or anybody unhappy? This would be a bad start for the week. Everybody happy with the suggestions? That's the easy one. Nobody says anything, so everybody's happy. Is there at 4 o'clock another course here? Should we get out by 4 or before 4? We should go down now. Okay, good. So, maybe I'm out in a second. So, here a very polar bond. So ruthenium catalysts are typically very useful for polar bonds. So if you remember the substrate scope here a bit, this is all ketone reductions. As well the other Noyori, that B catalyst, these are undergoing very easy ketone reductions. None of the others that we discussed had all ketones as substrates. Wilkinson and Crabtrees typically go for olefins. I'd be happy with Noyori. Either one could be the BINAP, would probably work too. This one here, we'd need something chiral. Could be the ruthenium BINAP, could also be, I'm nearly done, could also be something of that kind. Like, where is it? The diphos, where principally we have a chiral pocket, a chirophos, so it's a Wilkinson catalyst with a chiral pocket. Then, what do we had here? A cis olefin. Definitely we want to have something that doesn't attack the inner one, but then there's no stereoselectivity involved here, so that is easily accessible. Wilkinson is good for cis. I would have said palladium and carbon may work for this one here, because the surface can easily be reached by a cis olefin. This one here is very hindered. It's very difficult, and if you think of this as a three-dimensional structure, that olefin is kind of buried into an organic pocket in an organic cloud. So I think that here palladium and carbon here may work, because the cis olefin can somehow lie on the surface, but this one here, this inner one, is very difficult. So then this leads to Crabtrees here. Then just for the sake of completion, because we should stop, there's alternatives to direct hydrogenation, like the hydrosilylation, where we do it stepwise, where you have first the hydride and then a proton that we provide from different sources, which goes mostly with polarized bonds, ketones, polarized olefins or ketones. And then there's of course hydrogen transfer, which we'll go a bit through tomorrow. Very good. Thank you. Tomorrow we meet here, huh? Good. 10 o'clock. I try to be here at 10, I promise. Say? 9:50. 9:50. Okay, I'll be on time. I try to be here before 9:10. So if I'm here at 9:50, 9:55, we have time to lead it.
Okay, you can start.
Okay. So, apologies for the long break. So Chitin is very generous to me, because I arrived only this morning. So with the jet lag, it's about 4:50 in the morning now in my inner clock. I try to avoid this, so for me, try to make it lunchtime. So Chitin takes me to the nice places on campus to give me some exercise. So that may help. So anyway, apologies for the break. So we have, I understand we have at 12 o'clock we have to be out. So I may start a bit. I'd like to come back still quickly on the homogeneous heterogeneous question, because it's often a very relevant question for whoever works with catalysts. So how do we know whether a catalyst is homogeneous or heterogeneous? Typically we know by knowing what we put into the flask. You know, if we put a molecular complex in the flask, that should be homogeneous. It dissolves well, does the catalysis, so it's homogeneous. If we put some iron wire or some copper wire in the solution, it should be heterogeneous. Now, whoever has done some catalysis knows that this is a super oversimplification, and this is absolutely not true. So in the end, and I'll show you an example how we got initially in one of our works tweaked by a set that we had in our mind. We thought, oh, that must be homogeneous, it must be homogeneous, and we'll see the results in a minute. So how can we know for real? So this is all assumptive. If we say, look, we put in a complex that must be homogeneous. So how do we know? Luckily, there's a set of probes of how we can look at different working modes and to distinguish homogeneous from heterogeneous catalysis. I put them down here as late as we are. I don't know when you came in, just before we entered or a long while ago. You may have read most of this. Now, an important part is that there's not a single technique that is on its own unambiguous. So if we run a reaction, we need to probe it against 3, 4, 5 criteria to know whether it's probably rather heterogeneous or probably rather homogeneous. Just a single experiment taking out can be misleading. One is, of course, the visual appearance. If we get a turbid solution formed, if we get some black precipitate, if we get some visual decomposition, that may tell us it's heterogeneous. Still, we have to make sure that the precipitation or the perturbance is associated with catalytic activity. It could be also a partial decomposition that we observe, which leads to a heterogeneous, degraded, inactive product, and the reaction is still homogeneous. Then, if we have a clear solution, this is often a first hint that maybe the reaction is homogeneous. But again, we have to be extremely careful. If you put a glass ball of that size into a dichloromethane solution, you won't see the glass ball anymore, because it has the same refractive index, so that's it. So there could be huge particles in solution that we don't see. Nanoparticles, 2 to 5 to 10 nanometers, they're invisible by the eye, they don't sediment, they don't precipitate, so they're like a large a macromolecule in your solution. Totally homogeneous for the eye, not homogeneous for spectroscopy. So visual can be very misleading, can be a first hint. Poison. We can poison our catalyst with different additives. A heterogeneous catalyst is typically poisoned by mercury. So the poisoning, I'll come back to this in a second. The poisoning, heterogeneous catalysts typically are poisoned by elemental mercury. So, but that's only working for heterogeneous catalysts that form alloys with mercury. So, for example, for iron catalysts, for copper, we don't know about copper-mercury alloys. But for palladium, for rhodium, for iridium, we know that with mercury, the particles will be covered. So if you have some sort of a particle and you add mercury, the mercury will basically wrap the particle and shield all the active stage. So that's one way to, I'm nearly done back. Let me see whether I can.
Yeah, this is active.
Okay. So mercury can help for heterogeneous catalysts, for some heterogeneous catalysts.
I think the password was.
For homogeneous systems,
Yeah.
That's a reactivation. For homogeneous systems, we can typically use something that blocks the coordination site that is needed for the substrate to coordinate. Late transition metals are extremely phosphinophile, so phosphines are typically a good poison for homogeneous catalysts. We add an excess of phosphine, they'll coordinate to the metal center, that's it, the substrate is not competitive, that's it. Or very hindered olefins. For example, this diolefin has been developed as a poison for hydrogenation catalysts, for olefin hydrogenations, because these double bonds cannot be hydrogenated once they're coordinated, because they're in a rigid conformation when they're coordinated to the metal center. These cannot be hydrogenated. They cannot do the transformation that an olefin needs to do. And we'll come to this afternoon, how the hydrogenation works in terms of olefin coordination and olefin modulation within the coordinations. So that diolefin is blocked. And because it's chelating, it's even stronger binding, that's it, you kill hydrogenation activity. For this poisoning, we have to be very careful how we run the experiment. So ideally, we add the poison not at the beginning of the reaction, but somewhere at early stages of the conversion. So ideally, we add in a catalytic reaction, we add in this window the mercury or the phosphine. So that is when the catalyst is already active. If we add it at the very beginning, we risk that we block the catalyst activation, but not the turnover. So there we have to be extremely careful. Just to make this clear, the catalyst, the poison can interfere here. And then it's actually not poisoning the cycle, but it's poisoning the activation. And that holds both for the mercury experiment as well as for the phosphines and so on. So ideally we run two parallel reactions, and at the time x we determine the conversion, and to one batch we add the poison, to the other one we don't. And if it's effective poison, one batch will do this and the other will develop further. And then we can get some indication about the poison. So we have to be extremely careful. We also have to describe this very carefully. And we cannot run just one equivalent. We need a massive amount. So mercury typically is, mercury is typically added like 1,000 equivalents. So a good drop. You may get a reduction in conversions because with the drop of mercury in the solution, we may have mass transfer limitations, because the steering is not as efficient and so on. Kinetics are often a good indicator. Kinetics there should be saturations, there should be, so we should have saturation kinetics in a homogeneous phase where we suddenly get the substrate limitation. We should have especially reproducible kinetics. So if we run the reaction 3 times, we should have about the same turnover frequency, the same slopes. In heterogeneous systems, we have much more of sigmoidal plots, where the reaction starts at some point, then takes off to reach a classic curve. But this starting point may not be that reproducible, because the heterogeneous phase needs to get into the active state, and we don't know, typically we don't control catalyst deactivation or catalyst degradation. So this is an arbitrary point off. Can be once after 10 minutes, once after half an hour, once after 2 hours. And so that tells us then that it's not a programmed deactivation, but something that is out of our control, so likely heterogeneous. We have to distinguish this from the induction period that we see with some catalysts, where we need to activate the catalyst, and that may take time and thermal activation, for example. So we may have a bit of a lag time. But if this is but then this may be totally reproducible. Do we have to close soon? Huh? Oh, we have another 5 minutes. But 5 minutes to empty the room and then to go.
Yeah, I think.
So will we continue this afternoon? I hope I'll be more on time this afternoon.
Yeah.
Really sorry for this morning. That has had a few interruptions, but so we're here again at 2 o'clock. Or we're in a different room.
L4. So somebody will answer. Because we really didn't.
So if I'm late, I have no time to.
Take the activity, we couldn't get the same room for all the talks. But then we moved to L4. Our maximum talks will be in L4. Okay? And of course, we will be more on time. He just came only today morning, so I thought we will start a little slow and then we will move on. Participants who are coming from outside, you can take your lunch at hostel. That's what I think. If there are any other issue, you can come to Mandeep. She will take care of the other issues. And I think that's all. But please assemble at L4. If you have any other issue, please let me know or let Mandeep. Thank you all for coming. Particular thanks to people who are coming from outside the institute. I hope you got your accommodation if anyone is coming from outside. Martin, thank you very much. It's quite far. We are very glad that you are here, and we look forward to the course. You must have seen a little bit about the course. What is the purpose? Why our government introduced this thing? So that they wanted people from abroad, experts from abroad can come and give lectures on specific topics which we lack probably in this country. And this is also a good opportunity for even teachers from different universities and colleges from the far away place to come here and attend these lectures. I will not have more details because he will be here for 4 or 5 days, so you can interact with him anytime you want. And also I would suggest that there are many hours of courses, so make it as easy, comfortable, simple as all of you can make it. And please decide when you want break and all those things. I think Mandeep is there, so please you also arrange tea, coffee, whatever things you need. So I think with this we'll start the proceeding.
Thank you. So if we make it as comfortable as we can, we just wait till G10 is leaving and then we go somewhere to the bar. So thank you for the invitation, really. It's a great honor and privilege to be here. It's great to have this opportunity. It's not the closest, it's not around the corner to visit here, so it's a privilege to have this opportunity. We decided on the topic of this course a bit together, so that was it was the two of you and me that discussed a bit what could be the general topic of this course. We decided on going for sustainable chemistry through catalysis, so catalysis will be the key topic here. We're looking at this from a more organometallic inorganic point of view, so the metal will always be in the center. So we look a bit at mechanisms, we look a bit at concepts and principles, and then develop this into processes. Now I've never done such a course before, so I'm very much dependent on your feedback, on your interruption, on you asking and you participating. So if I'm too trivializing, if I go on things that you know already for years and years, tell me and we can move on. So that's much better than you getting bored and you're starting to sleep and snore and I don't know what I'm doing. But at the same time as well the other thing, so if I jump, for whatever reason I jump too quickly, let me know, tell me I don't understand that thing. And then we can evolve a bit further. The good thing about having these 4 hours now for the next 4 days is that we have plenty of time. And I put together a bit of a program, but that's not compelling at all. That's not, we can always skip a few or move fast forward. there's no end really. So that's it. So sustainable chemistry through catalysis. Before I start, I thought I'd let you know a bit where I'm coming from as well. If my accent is for whatever reason a bit weird, let me know. So then we can, either I go slower or I write it down and then maybe we have some recognition. So that's the University of Bern. That's actually from the landing where our labs are. So that's a picture taken from our labs. This is just a few houses from the district, just behind this central station of the city of Bern. Bern is the capital of Switzerland. Switzerland is somewhere in the middle of Europe, so I don't know how good your geography is. Now the nice thing about the city of Bern is that we have high mountains, but then coming here and talking about high mountains, this is a bit ridiculous because our mountains are about half the size of your mountains. So still we're very proud of having 4,000 meter high mountains, so that's what we see then. So not that it feels like Himalaya, but it feels a bit like, at least there's some snow. So what brings me over, this is actually a picture taken 16 hours or so ago, so from Switzerland coming over here. There's a few connections, and one of the connections between India and Switzerland, I don't know how many of you are into sports, but then one connection that unfortunately got broken up again, you may remember those two ladies, they won in no time about everything they could, and even so they have been, at least some of them have been on break. Good. So that's a bit of giving you a bit of maybe a rough connection of where we are at. So what are we doing in the next 4 days? So why did we choose that topic? What is the motivation of looking closer into catalysis? And I put a few comments together of what is motivating us to study catalysis and to try and advance catalysis. And I think that has as well been the major part of starting this course. So we know that every prosperous economy, every modern society is extremely dependent on catalysis. Catalysis is really a driver of prospering economics in a country. Of course, we're not talking here about law and about financial stock markets or so, but about having sustainable productivity and having productivity that can export, that can generate welfare and income.